So this is experiment number 9. I will leave this up tomorrow because I know we don't have a lot of time, and if you're drawing it out, that's, I'll bring it back up. I'll have it. But here's the can, and this is air particles inside. And then there's water at the bottom. Okay? Then I put it on the hot plate. And if you see it on the hot plate, the air molecules on the outside are actually applying pressure to the can on the outside. So there's actually pressure on the outside, and we can see that by these arrows that are hitting the can on the outside. And that represents pressure. The more arrows I have, the more pressure that I have. On the inside, I have about the same number of arrows that represent air and water. So if you notice, when I get you put on the hot plate, what's happening to the water? It's going up, and we see that as steam, right? And so there's steam inside here. So there's steam inside here. And it's spread out because steam is a gas. And the water's all gone. So the water that's down here originally is now all gone. And some of it, or a lot of it, has escaped out of the top. Okay, so then I put the can inside the water, and real quickly that steam, what happened to the particles of water that was steam? Where did it go? It went back and condensed into the water because the water's cold. And so the steam now goes back into liquid form. Okay, so then when you look on the outside of it, do you guys see why there's more arrows on the outside than inside? These particles, there's only 3 left. So these original 3 here are still in there. But what happened to all of these that were in there that applied pressure to the inside of the can? They are now outside of the can out here. So it leaves empty space. And what do we know about empty space and the pressure with empty space? So if we don't have molecules moving around and hitting, what do you think is going to happen to the pressure? But inside, when I say the pressure inside compared to the outside, what's the pressure inside going to be? Less. So it's going to be less because you need to have collisions to create pressure. And if you look inside here, we only have 3 molecules that we're showing actually applying the pressure. At the beginning, over here we had a lot more collisions taking place. Okay? Now the pressure on the outside, did it change any? During the experiment, does the pressure in the room change any when you put the can in? No. So, what happens, there's more pressure on the outside, acting on the outside, and when we don't have as much pressure on the inside, do you guys see why it collapses? Okay. So, I could actually write out a statement. I don't have enough time now, but I'll show you the statement tomorrow. Of saying that what happened to cause the can to crush was the water boils and it pushes the air out. So it pushes air molecules out. It leaves less air molecules behind. Since we have less air molecules behind, we don't have as much pressure on the inside of the can versus the outside of the can. And because of that, the outside pressure is greater than the inside pressure and the can collapses. And that's what that's your reason for that phenomena. This is called the phenomena that it's like, why does the can crush? Well, this is why the can crushes. This is my reason for it.
What would happen if you had more water in it?
If you had more water in it, I don't think it's going to... I think it might be a little less collapsing because not all the water will evaporate out.
Oh, less will get lost.
Yeah. But if you let it all go out and it doesn't have any other water in it, then a lot of the steam will go out and then the air would come back in. So the air would actually come back in. But when you see it steaming, it's pushing out what? Water and air, both. So then when you turn it upside down in the cold ice water, that means it condenses quicker. So when it condenses quicker, then it collapses. So that would be what you would do is you go, okay, we put it on the hot plate, we put it in the water, the steam condenses, it leaves behind fewer molecules, and then we get a good crunch on that. Okay? So that's what I'm going to have you do on some of the other ones. Some of the other ones are a little bit more difficult to do, but there are some, like the balloon would be an easy one to do, the syringe is an easy one to do, the one with the pop can or the pop bottle and the balloon, those two are easy to do, I think, compared to some of these with the water in them, and why it doesn't drain the water out, and we can talk about those tomorrow. So tomorrow we'll have time for you guys to finish up your discussion on this lab. Okay, we'll see you. Good job of finishing up.